This video will focus on the learning target. I can compare the rates of effusion and diffusion. So just a reminder, diffusion is when gases move from high concentration to low concentration, and effusion is when they move from high pressure to low pressure. Now, what's slightly weird about this topic, as opposed to everything else we've done in gases, this is the only topic where the actual mass of the particle matters. Okay? When it comes to pressure, volume, temperature, and mole relationship, it's all based on the number of moles, which doesn't take into consideration the mass at all. Okay? When it comes to effusion and diffusion, though, the speed at which they're able to move, which is rate. Rate is a speed measurement. So the speed at which they're able to move either from high concentration to low concentration or from high pressure to low pressure does have a relationship with its size and its mass, which should make sense to you, again, dealing with the practical world. You know, a heavier object, in general, it takes more energy to move it, so it's going to move more slowly. And a faster particle moves more quickly. And that's also true with diffusion and effusion. When we have a lighter particle, it will move more quickly as it disperses, where a heavy particle will move more slowly. So there's a law called Graham's law that relates the rates at which two different gas particles move to one another. And if you read this definition right here, it says the rate is inversely proportional to the square root of the gas's molar mass. What that simply means is if you are comparing rate at which gas A moves to the rate at which gas B moves, that's going to equal the square root of the molar mass of B divided by square root of the molar mass of A. So you see the inverse proportionality there, because in terms of the equality, your designation for A and B flip. So while the rate of A is your numerator, the molar mass of A is your denominator, because it's the rate and the mass is inversely proportional, which means the heavier you get, the smaller your rate, because a really heavy number in the denominator is going to make that ratio smaller, thus decrease your rate. Okay, so the smaller the mass, the bigger the rate will have. That's the only trick to this equation, is remembering that it's a square root and remembering that you flip A and B. So here are two different Graham's law problems. One asks how much faster does nitrogen effuse than argon, and another one actually asks you to identify a gas. In terms of faster, we're comparing rates. Okay, how much faster does nitrogen than argon means we're essentially getting a ratio of rates. We want to know the rate of A as it relates to the rate of B, which means that nitrogen is going to have to be my A and argon by my B, because when you get a number out then, so if you get the number 4, that means nitrogen will be 4 times faster than argon. If you flipped it instead, if you put argon on top and you got a measurement like 4 or 3, that means it's actually the inverse to get the relationship. So realize whatever you're referencing should be your A. How much faster is nitrogen than argon? A is going to be nitrogen. So the rate of A versus rate of B is going to equal the molar mass of B, and we've said B now is our argon gas. So this is going to be the molar mass of argon, which is 39.95, and that's going to be divided by the square root of the molar mass of nitrogen, which is nitrogen gas, so diatomic, which is going to be 28.02. If you solve for that then, you should get 1.19. And again, what that means in relation to rate is that nitrogen moves 1.19 times faster than argon, because what I've solved for is a rate ratio. What is my rate relationship between the two? The second problem here, identify the diatomic gas that measures 3.984 times faster than oxygen. Okay, so that 3.984 times faster is my rate relationship now. That is my rate of A. My rate of A is 3.984. So I'm going to put that on top. And my rate of oxygen then is 1. That's your reference. You're 3.984 times faster than whatever your oxygen is. So now the only trick to this is to remember what the relationship is. They relate inversely, so diagonally. So the molar mass of oxygen, because this is the rate as it relates to oxygen, and this is the rate of my unknown gas, so my molar mass of oxygen will go here. And then my unknown molar mass of my diatomic is right here. Okay. So now you just solve for it by cross multiplying and dividing. 1 times the square root of this times those, divide down, and you're going to isolate that question mark, remembering to square both sides to get rid of the square root. If you solve for this unknown molar mass right here, what you'll get is 2.02 grams per mole. So the question then becomes, what diatomic gas is going to have that molar mass? That's going to be hydrogen. Okay, so it's 2 different types of problems you can do in relation to diffusion and effusion using Graham's law. The other mathematical relationship we can do in relation to each individual gas is something called partial pressure. And this is really straightforward mathematically, but conceptually you can do a lot with it. And it's just the idea that the pressure of whatever the gas system is will be the summation of the pressure of each gas. So if you know the pressure due to oxygen in the atmosphere and the pressure due to nitrogen in the atmosphere, and you add them all together, you should get the pressure total. Okay, so this is one that Dalton came up with, John Dalton, our guy back for our atomic theory. And again, it's really straightforward, like a lot of the stuff he did, but it seems counterintuitive because you'd think some gases would contribute more than others because of their size, when in fact they don't. Okay, the size of it really doesn't matter in terms of their force. That's it for this topic. Have a nice night.